Last time we talked about the moon and its phases and how the moon is responsible for eclipses. And before that, we talked about what you could see with the naked eye, and those are all things that ancient astronomers were able to see. So we're going to continue along that thread of what ancient peoples could see and how they started to explain what they could see in the sky. So today we're going to be talking about ancient astronomy, what they observed, and we'll talk about how they were able to do some pretty interesting calculations. Okay, so now we'll transition to talking about other things in the sky that move differently from stars. And we now know that those things are planets, but when people started noticing these things, they didn't know what they were. So these are the objects that ancient astronomers knew about, and they gave them importance because they move differently to the rest of the stars in the sky. And so we now know them as planets, and they identified Mercury, Venus, Mars, Saturn, and Jupiter with their naked eye. So just looking up at the sky and seeing what things move differently than the rest of the stars. Mercury is tough to see. It's always very close to the sun. So sun is just set here, and then Mercury is about to set very soon after that. Venus is very bright, either in the end of the day or in the early morning. Mars looks pretty red in the sky and is decently bright. And then Saturn and Jupiter are very bright in the sky, and they are also higher up in the sky than the planets that we now know are closer to the sun. The way that planets move in the sky is different than stars because of what's called retrograde motion. So throughout the course of the year, things do move through the sky. And so if you plotted the location of Mars at the same time of night every night, you would get something that looks like this. You would expect the motion to kind of follow this straight yellow line, but instead it does this little loop-de-loop, in this case over the course of a few months, before returning back to this kind of predictable line that it should be traveling on. So this is the motion that makes, part of the motion that makes planets different than stars in the sky. But now ancient astronomers have to figure out, how do I explain this motion? With our current understanding, we know that this retrograde motion is a result of, so everything is orbiting the sun, the Earth is orbiting the sun, and Mars is orbiting the sun. The things that are closer to the sun orbit faster, and so at position 1, the Earth has not caught up to Mars in its orbit, but since it's faster, eventually it will catch up to Mars and pass it. And so it's that consequence of the Earth catching up to Mars and then passing it that causes the retrograde motion. So the way that we determine the position of something in the sky is due to what stars are behind it, basically. So at position 1, it looks like Mars is in the constellation of Gemini. At position 2, it's near the constellation of Cancer. At position 4, it's got the constellation of Leo behind it. Position 3, Leo. Position 4. Now it looks like it actually moved away from the constellation Leo. And at position 5, now it's back in the constellation of Cancer, even though that's the opposite direction of the way it was moving previously. Then at position 6, it's back into Leo, and at position 7, it's about to leave the constellation of Leo. So this is how we explain retrograde motion today, but ancient astronomers did not have our understanding of the workings of the solar system. So retrograde motion is caused by us passing that planet, or if for the interior planets, them passing us in their orbits. And we'll talk about what the theory that ancient people came up for explaining retrograde motion later. The big reason that they rejected this idea that so the underpinning of this theory is that the Earth has to orbit the sun. The reason that ancient people rejected that idea is that they don't see what's called stellar parallax, or they couldn't see it with their naked eye. So if the Earth was moving, then you should see nearby stars appear to change position in the sky. So for example, in January, you would expect to see this nearby star kind of on the left side of this group of stars. And then in July, you would expect to see that nearby star appear to shift, and now it's on the right-hand side of that group of stars, just due to the angle that you're looking at that star changing. It turns out stars are really, really far away, and so we can't measure the stellar parallax with our naked eye. With telescopes, you can see this parallax. You can't see it with your naked eye. And so ancient people rejected the idea that the Earth goes around the sun, and it caused centuries of delays in our understanding of the universe. So there were people that did think, like Aristarchus, thought that the Earth did go around the sun, but the majority of scientists and people did not agree with that hypothesis. To review, there were three motions that the Earth does. It spins around on its axis, it orbits the sun, and then its axis of rotation precesses over a 26,000 year period. So that caused the constellation, where the North Pole is pointing, to change into different constellations on the sky. The phases of the moon are caused by the moon orbiting the Earth. And then there were three conditions that you needed in order for an eclipse to occur. So let's see if you guys remember what some of those conditions are. And for this one, we'll only think about two conditions that you need for an eclipse. Okay, so the three conditions were for a solar eclipse, it has to be a new moon, and for lunar eclipse, it has to be a full moon. So that leaves you with only two choices left, the yellow or the blue. And then the third condition was that the moon has to be at its closest point to the Earth. So the moon-Earth distance matters, but the Earth-Sun distance doesn't matter. So the three conditions are new moon for solar eclipse or full moon for lunar eclipse. Then the moon has to cross the ecliptic, so it has to be in the same plane as the Earth and the Sun. And then the third condition is that the moon has to be at its towards its nearest part of its orbit. It doesn't have to be exactly at the nearest part of its orbit, but it has to be pretty close. So that was our review. Now we'll talk about kind of how astronomy is one of the most ancient of sciences, so we'll talk about how ancient people did astronomy and then how that kind of led to the development of our current scientific method. So the way that we use scientific thinking now is really just a process of trial and error experiments. So you kind of you use your experience to decide how to improve on each of your individual trials and what to change, but it's basically just trial and error is how we do science. So astronomy is one of the oldest sciences, and there are a lot of applications that people have used astronomy for in the past. So you can keep track of seasons, and that's really important for doing agriculture. So how do I know when to plant my crops or when to harvest them before a freeze comes? And then it had importance societally for religious and ceremonial purposes. And you can also use the stars to help you navigate. So if you're trying to cross the Atlantic or Pacific Ocean and you don't have GPS, how do you know what directions you're going and where you are on the Earth? So astronomy is useful for all of those things. Okay, so last time we talked about how in the northern hemisphere, if the side of the moon that was illuminated was on the left side or the right side, you could determine whether it was a waning or a waxing moon. But that only worked in the northern hemisphere. If you're really close to the equator, it won't be the left or right side of the moon that's illuminated, but it'll be the top or the bottom side, or top or bottom part of the moon. And then when you go into the southern hemisphere, it flips. So whichever one was right side was waxing in the northern hemisphere, the right side will be waning in the southern hemisphere. And also so if you took a picture of the moon in the northern hemisphere, and then you took a picture of the moon from the southern hemisphere, the images would be upside down compared to each other. So you still see the same face of the moon in the southern hemisphere, but because you're standing on a sphere and your head is facing down versus facing up in the northern hemisphere, the moon looks like it's upside down if you compare northern and southern hemisphere. Okay, anyway, so near the equator, the light side of the moon and the dark side of the moon is top versus bottom, and you can use the angle of the crescent in those different months to determine what time of year it is. So if you've ever lived near the equator or visited, you'll know that the temperature doesn't really change a lot. So if you're far away from the equator, it's easy to tell, like, oh, it's really hot, it's summer, it's really cold, it's winter. Near the equator, you don't have those kinds of big temperature swings. So how do you tell what time of year it is to determine when do I plant my crops? So if you live somewhere near the equator with a wet season and a dry season, then you can use the angle of the crescent moon to determine when is planting season, when is harvest season. But the only way you can do that is by taking very careful observations of the moon and how it looks on the sky, and then correlating that to your rainy and wet seasons. We talked about how the reason that we have 7 days in the week is because there are 7 objects in the sky that move differently than the background stars. Those are the sun and the moon, and then the rest are planets. So Mars, Mercury, Jupiter, Venus, and Saturn. The names of these, so they correlated these objects to deities, and so we speak English, which is a Germanic language, and that has a lot of ties with Norse languages, and so things like Thursday is really Thor's Day, and so that's how we get our English names for the days of the week. Freya is a goddess, so her day is called Freya Day, or in English, Friday. If you speak Spanish or French or one of the Romance languages, then it's really easy to draw the parallel to the Roman gods, like Mars becomes Mardi for Tuesday, etc. So all the days of the week are tied to the 7 objects or 7 wanderers that move differently compared to the background stars. And these are all the planets that you can see with your naked eye. So we've talked about how ancient Egyptians used sundials to keep track of time during the day. You can use by looking at the moon, you can track the angle of the crescent moon to decide when it's going to be rainy season or dry season. They kept track of where the planets would be over the course of the year, and ancient people were actually able to predict eclipses. So we saw those maps with the different paths that the eclipses would take over their long time period, and ancient peoples were actually able to predict eclipses as well. So they were able to do a lot of stuff just by taking careful observations and doing that over many years. So here's a picture of an obelisk in Egypt that you can use as a sundial. So wherever the shadow is being cast, that will give you a time of day. So you could imagine drawing starting from, I guess, maybe 6 a.m. when the sun rises, and then labeling the different parts on the pavement with different times to give you a clock that you could use before you invented things like gears or batteries to power your clock or your watch. Stonehenge was completed around 1500 BC, and there's several different alignments that happen in the sky that correspond to how the stones in Stonehenge are arranged. There's other stones, so this is an even older stone circle in Scotland that's 4,000 years old, and the moon rises in a very specific part in the stone circle on an 18.6 year period. The Aztecs built their step pyramids in alignment to positions of things on the sky. In Peru, there's a lot of buildings that have alignments with things in the sky. And then what I think are even neater in Peru are the Nazca lines. And so these are huge shapes that are basically carved into the floor of the desert that have survived for thousands of years. And we think that these are basically the constellations that they were tracing onto the ground in the desert. And they've survived for so long because the Atacama Desert is very dry, so it's not going to get washed away. There's very little wind, so it's not going to get blown away. And so there's several of these giant shapes carved into the desert, and they line up with patterns in the stars. In North America, there's carvings in the rock, so this is a spiral pattern that lines up exactly during the summer solstice. And so there's a lot of these examples where ancient people have built, in this case, Machu Picchu, which is a city in the Andes Mountains. And again, they built this city so that it lines up with the solstices. So in order to do these really big engineering projects to line up with these celestial events, you have to have a very good understanding of astronomy, basically. The people in the Pacific island cultures, like the Maori, were very good at navigating by the stars. So here's an example of a technology that they could have used. So this is basically like a star chart. So this pattern is set up in such a way that you can align it to the sky and use that to navigate by the stars. And so these people were able to colonize the whole of the Pacific Ocean, basically, before there were compasses or GPS. And those are very small islands in a very big ocean. So it's very impressive that they were able to do this using their knowledge of the ocean and the stars. In China, in the year 1400 BC, there is evidence of people writing down an observation of what we now know as a supernova. So there was a very bright new star in the sky that lasted for some amount of time, and if you are people who look up at the star every night, it's going to be very apparent to you, oh, that's new, and there isn't usually something new in the night sky hardly ever. And so that's very important, and you're going to write down your observations of that event. So humans have been looking up at the sky for basically our whole existence, and a lot of the techniques that we'll talk about for how you do science really originated from this practice of these repeated observations of the night sky. So now we'll focus on a specific ancient culture, and those are the Greeks. And we'll talk about why Greece is kind of where we trace our modern scientific understandings from. And then we'll talk about the model that they developed for explaining the retrograde motion that we talked about earlier. So the cradle of human civilization really started in the Middle East and Mesopotamia, and then basically spread out from there. So this was the first region where humans developed their civilizations. And so that's really the basis for a lot of what humans do currently. But we kind of trace a lot of stuff back to the Greeks because they were the first culture that developed what we call models. And so a model is just you come up with some idea that's testable for how natural phenomenon occur. So this is different from, say, I think that an earthquake happened because a god was angry at me and we didn't sacrifice enough stuff, so the earthquake was a punishment. Versus, I think that there are these things called plate tectonics that cause that all the continents sit on top of, and when they shift, that causes earthquakes. So this is where we separate kind of spiritual or religious thinking from what we call scientific thinking. Okay, so one of the models that these ancient people came up with was that the Earth is round and it's spherical. So this is something that they had thought for a while, and Eratosthenes is the Greek philosopher, mathematician, that came up with a way to calculate the radius or circumference of the Earth. And so we've known that the Earth was round for a very long time. So what the story goes that he heard from someone in Egypt that there was a town where at noon on a certain day of the year, there were no shadows cast from objects. So that would imply that the sun has to be directly overhead at noon on those days. So if you go outside at noon today, even though you think the sun is at its highest point, it's not actually directly overhead. There's going to be some shadows cast. So that city was called Syene, and Eratosthenes was in Alexandria, and so he paid someone to measure the distance walking from Alexandria to Syene. And the way that they measured distances back then were there were these people whose jobs it was to walk between different places, and they were very careful about how they walked and were very good at counting their steps. And so they basically had someone walk that distance, count their steps, and that was the distance measured. And so they measured distances back then in what are called stadia, and we think that the stadia is about 1/6 of a kilometer. And so you can take the distance that they measured between the two cities, and on the next slide we'll see the geometry for how we do the calculation. But taking that distance, they were able to calculate, or Eratosthenes was able to calculate an approximate circumference for the Earth. So the number he came up with was about 250,000 stadia, and if we convert that using this conversion factor, that's about 40,000 kilometers. We now have much better technology that we're able to use to measure the circumference of the Earth, and our modern measurement for the circumference of the Earth is about 42,000 kilometers. Oh, sorry, I had that backwards. He measured 42,000 kilometers, and our modern value is 40,000 kilometers. So he was very close. So 2,000 kilometers out of 40,000 kilometers is less than 10% error. That's like 5% error. So that's really good for having someone walk between two cities and count their steps. So here's the geometry that he used. So you know that in Syene, so that's the right-hand obelisk, there's no shadow. So you could draw a straight line from the center of the Earth all the way to the sun, and those objects would be lined up. Then in Alexandria, on the same day, he measured that the angle of the shadow cast by an obelisk in Alexandria was about 7 degrees. And so using some geometry, if you know the angle, this red angle at the top is 7 degrees, then you also know that this red angle in the bottom is 7 degrees. And so with those two angles, you can now calculate the radius or circumference of the Earth. So let me do that on the board. Okay, so we've got this angle is 7 degrees, and we know the distance that was measured. was 5,000 stadia. But what if we completed the circle? So we think the Earth is spherical. So this angle to this distance on the surface of the Earth, let's make that a fraction. If you went all the way around the circle, what would that angle be? Yeah, 360 degrees to go all the way around. And so now, the only thing we don't know is the circumference. So we've just set up a ratio between the angle between Syene and Alexandria, and we had someone walk 5,000 stadia and measure that distance. So that's one ratio. And then the other ratio is the 360 degrees to the circumference of the Earth. And so if you solve this equation for C, so 360 divided by 7 times 5,000. So if you plug that into a calculator, you would get the circumference of the Earth as calculated by Eratosthenes. So just by understanding some geometry, he was able to calculate the circumference of the Earth and thereby the radius of the Earth. So that's pretty incredible for someone doing science 2,000 years ago. Okay. The next thing that ancient Greeks were able to measure was the distance between the Earth and the Moon. So measuring the circumference of the Earth is pretty incredible, but how are you going to measure this really long distance between the Earth and the Moon? So what they did was they used the lunar eclipse. They used lunar eclipses. So you know how long it takes for the Moon to orbit the Earth. So that's based on the lunar cycle, so that was about 30 days. So that's the total time it takes for the Moon to go around the Earth, around this big circle with radius big R. You can also time how long it takes for the Moon to pass behind Earth's shadow during a lunar eclipse. So again, we now have another ratio that we can set up. On the left-hand side, you have the circumference of the orbit of the Moon, so the distance that the Moon travels to go around the Earth, divided by the time that it takes for the Moon to go around the Earth. Then you have the distance that the Moon travels to as it passes behind the Earth's shadow. So the Earth is a sphere that has a radius little r that you could calculate using Eratosthenes' measurement of the circumference of the Earth. So in order for the Moon to pass from just outside of the Earth's shadow to the other side of Earth's shadow, it has to go through 2 times the radius of the Earth. And then you time little t, the amount of time it takes to do that. And now you have another ratio where you can calculate the distance big R, which is the distance between the Moon and the Earth. And I don't have the value of the measurement they did for this, but again, it was very close to what we now know is the distance between the Earth and the Moon. And so again, they were just able to do some geometry and set up a pretty simple ratio to calculate what they wanted to calculate. The last thing that they measured was the distance between the Earth and the Sun. So the radius of the Earth is pretty small compared to the distance between the Earth and the Moon, and the distance between the Earth and the Sun is way bigger than the distance between the Earth and the Moon. So this time, instead of a simple ratio, we have to do some trigonometry. So on the Earth, in this picture, they're seeing a specific phase of the Moon. They're making this dotted red right triangle. They're making it a right triangle here at the top left corner. And so then from the Earth, you can measure the angle between the Moon and the Sun on the sky. And so that's what's in this thought bubble here. So you could imagine, we talked about how if you use your fists, that's about 10 degrees on the sky. And so if you use your fists to measure the distance between the Moon and the Sun here, you have some angular distance. So that's the angle theta down here. We just measured the distance between the Earth and the Moon on the previous slide. And so now we have an angle and one side of a triangle. So we could calculate this distance x, which is the distance between the Earth and the Sun. And so the angles that we have mean that we're going to use cosine as our trig function. And you can solve this trig function for the distance x between the Earth and the Sun. And so again, they got a pretty accurate measurement for the Earth-Sun distance using just a simple geometric setup. So the ancient Greeks were able to do a lot of really cool stuff just by making observations and using a little bit of understanding of geometry. So that brings us to the kind of one of their mistakes. So we talked last time about retrograde motion, and now we're going to talk about how ancient Greeks, what model they came up with to describe that retrograde motion. Part of their part of the reason they came up with a flawed model were they came in with some assumptions that are not necessarily correct or founded in any scientific reason. Earth being the center of the universe, we'll talk about why they thought that would be the case. But then they came up with this other idea that everything in the heavens or in the sky had to be perfect spheres that moved on in perfect circles. So the top one, they actually had some observations that might support that the Earth was the center of the universe. But this last one was just their appeal to perfection, basically. If you think the heavens are where your deities live, or you think the heavens are perfect, then you are going to assume that everything about them is perfect. And as it turns out, that is not going to be the case. So before we talk about what the ancient Greeks came up with for retrograde motion, let's see if we remember what our current model for explaining retrograde motion looks like. So which of these analogies best represents retrograde motion? Yeah, so the way that we currently understand retrograde motion, if we imagine the sun is at the center of a racetrack and all of the planets are cars going around that racetrack. And when one planet or car passes another, then we get this apparent retrograde motion. So this was the picture that we had last time. So the Earth is closer to the sun than Mars is, and we'll talk about next week how that means the Earth is going to orbit faster than Mars. So the way we determine something's position in space is with respect to the background stars or constellations. So at position 1, the Earth, when we look at Mars from the Earth, we see it, and it appears as though Mars is in the constellation Gemini. Then at position 2, it looks like Mars has moved to the right or to the left of the constellation Cancer. Then at position 3, it's almost in the constellation of Leo. But at position 4, when we've now caught up to Mars in our orbit, now it looks like Mars has gone back towards Cancer a little bit. And that's not how anything other than planets will move in the sky. So that's very strange. Then at position 5, it looks like Mars has moved a little bit more towards Cancer. But then at position 6, now we've just about completely passed Mars in our orbit. So it looks like Mars will start going back towards the left again, towards Leo. And then 7, even further left, leaving the constellation of Leo. And so this retrograde motion happens for about 10 weeks whenever one planet is passing another planet in its orbit. So Ptolemy is the Greek scientist who came up with a model to explain this retrograde motion. And what he came up with was actually pretty good, and it was in use for the next 1,500 years. So basically until the Renaissance era, this was the understanding for how the heavens moved. And so the model that he came up with, Ptolemy's model, was basically that, so first we're going to put Earth at the center of the universe, and then the planets go around the Earth in a circular path, but along that circular path they're actually doing circles around some point in space. So these are called epicycles, and so you can basically think of this as the big circle is their orbit, and then the planet is orbiting that big circle on these small little circular orbits. And so if you track the position of the planet, for the most part it looks like it's just orbiting the Earth, but at one of these epicycles it will look like it doubles back on itself, and then it goes back to its normal path. And so this is this little part of its orbiting the smaller circle gives you what appears to be retrograde motion. And so you've got this big circle is the path around the Earth, and then along that big circle it's doing these small little loop-to-loop circles as it goes. And so here's what one of those epicycles would look like for just one planet. And the gray line is the path that the planet looks like it travels in the sky. You're not able to see the blue lines in the sky. And so you can set up your epicycles to give you however many periods of retrograde motion you need. So that particular planet had two little loop-de-loops, and so that was two periods of retrograde motion that you would observe. And so here's the full model, including things like the sun and the moon. So again, we're putting Earth at the center of the universe. The moon goes around the Earth, but it doesn't do epicycles. It just orbits normally. Then the next out from the moon is Mercury. So Mercury does epicycles. Then next out from Mercury is Venus. Venus does epicycles. Then next out from there is the sun. The sun does not do epicycles, so it doesn't do retrograde motion. And then Mars, Jupiter, and Saturn all do retrograde motion on epicycles. But then further out than that, the stars don't do retrograde motion. So there's some, according to the Ptolemaic model, there's some that do retrograde motion and some things that don't. And you can actually use this to predict decently accurately where things are going to be at any given time in the sky. So here's a video of the full model with all of the different planets. And so you can see different planets have different amounts of epicycles that they do. So Mars has 5 epicycles. The next out from there is Venus. Venus only has 2 epicycles. The next out from that is Mars. Mars only has 2 epicycles. Then further out from there, you get Jupiter that has a lot of epicycles, but they're very slow. And then Saturn, even farther out than that, a lot of epicycles, a lot of retrograde motion, but again, very slow orbit around the Earth, because again, they thought the Earth was the center of the universe. I think it's a very nice theory visually, and like I said, it does explain some of the phenomenon that we see in the sky, and it makes decent predictions for where an object will be at some future time in space. But we'll talk about next time how there are some observations that this model cannot explain, and that will lead us to a new and better understanding of astronomy and science in general. So if you are a student of history at all, you'll know that the culture and society in Europe didn't last all the way from the ancient Greeks to today. And so a lot of the knowledge was actually preserved in the Muslim world and then reintroduced into Europe after the Dark Ages. And so science is not done just by one group of people, and it's not done in a vacuum. And there's a lot of interesting tie-ins between history and culture and science, and we'll get more into that next class. So the Greeks developed what we call models, which are things that you can use to predict future events, like the Ptolemaic model. You can use that to predict where planets will be in the sky at future times. And that model building is kind of our current way that we do science. So next time we'll talk about what model we came up with that replaced the Ptolemaic